I am Hamid Reza Marateb. I'm affiliated with the University of Isfahan, and I also work with the UPC. I am also affiliated with the Smart University of Medical Sciences in terms of AI regulation in digital health. And I'm going to talk about the robustness and how can we improve the robustness of our model when working on neural engineering. So first, we need to talk about the issue that why robustness is important. Okay, we deal with a very variable signal. You know whether you work with the neural signal or surface signal or intramuscular EMG signal, they are variable by themselves. They are the result of a stochastic process, and they have inherited variability. And we also deal with the measurement noise. It could be from the input as systematic noise, or it could be the output, which is called the measurement noise, which is recorded when you are recording any biopotential signal. So when you are dealing with the measurement noise, you are dealing with different electrodes. When you are designing your method on a specific electrode, and it should work in other types of electrodes or other conditions or various artifacts and electrode shifts. And when you design a system for digital health, it is very important to consider reliability in your clinical application. So when you design a product, then robustness enables it as a safe and trustworthy product, okay, for diagnosis or device control. There are various real-world examples that we can think about. For example, when you are designing a movement detection algorithm, it should work in various conditions. So the robustness is a key. So how can we bridge, our neural devices to the robustness? There are 4 keys in this chain. The first one is data. When you are working on data, you have to be careful about biases, and you have to perform bias mitigation. And there are at least 2 standards to use, and I will talk about them briefly. And when you are designing your model, you have to have a robustness planning. So you have to change the input, you have to add noise and variability of your data, and then you need to assess the accuracy drop rates and to see whether it is acceptable or not. And in this chain, if it's not acceptable, you have to change everything at the very beginning, from feature selection, feature extraction, or classification. So basically, it's a closed loop control where the output is assessed based on the robustness planning. And there are 3 standards in this area, which is TR 24029-1 and -2, and -3 is under development. So basically, they are mostly statistical. And after talking about them in general, I will go through the math and clinical aspects. So we will go from theory to practice, so you will know what to do for this. And the third point is the evaluation. It is very, very important to consider indices that are suitable for your problem, and you have to have a deep knowledge of biases when you are reporting the performance of your system to avoid biased indices. And number 4 is the governance. We talk about it in the framework of risk management and monitoring. You know, there are various management and monitoring indices for medical device and everything. And now for AI, we also have risk management, which is ISO 23894. And also we add another standard, which is related to the trustworthiness of AI system, because most of the AI systems are not trustworthy. So how can we include robustness? Based on the terminology of the ISO standard, the robustness comes from the performance under noise, domain change, or adversarial inputs. For example, when you design a system that identifies the movement, you have to check it in other types of electrodes. You have to induce high amount of baseline fluctuation and assess the outcome of your system. You need to incorporate electrode shift and then assess the dropped accuracy rate in order to make sure that this product works in practice. So with this simple example, you will be able to see various types of noise, artifacts, and even domain changes that must be considered for your closed loop design cycle. It doesn't matter whether you are working on waterfall design methodology or V-type or agile or any type of design methodology. If you consider robustness as a key item, then it will affect all of your procedures. But how can we do this? We might design our system after hours and days and weeks and months. And when we come up with the robustness at the end, we will see that it doesn't work and it's not robust. So what I would say as the best method is to consider the robustness as a design input before designing your system. So consider the robustness and just use features that are robust enough. Change your methodology to a robust way. I will talk about it in math and detail after this. Okay? So the best scenario is to consider all of these types of standards as a design input and consider them before designing your system. The worst methodology is not to consider them. Okay? So, and if you don't consider them, they don't work in practice. So, how can we assess the robustness? You know, we should consider it from various perspectives. The first one is the statistical perspective. You set an acceptable threshold for accuracy drop rates before running your experiment. It's not like you run your experiment after some perturbation and you see 15% of accuracy drop rate and you change your threshold to 20% to be valid. We call it in a statistic as p-hacking. You know, in p-hacking, it's like you change the significance level in order that your results seem significant or not significant based on your expectation. So first of all, you set a proper statistical threshold and then you use it by the end of the experiment. And then you also define the maximum stable space. You use a proper statistical way to tell the users under which condition your algorithm is robust enough. Okay, so for example, you model the entire procedure based on multiple linear regression or any type of statistical test, And then you say, if you are using our decomposition algorithm, it will work until the SNR of XXdB. Otherwise, we will have a drop in accuracy because of these perturbations. And then you need to deliver the scenario matrix, especially if you want to have a CE mark, or if you want to have a device that works in practice, then you provide your scenario matrix. And we call the scenario matrix that all types of perturbation are implemented once at a time, and they call it OAT. It's like you don't implement all the perturbation together. So you change one parameter and you assess the effect of the perturbation of that specific parameter, and then you report the accuracy drop rate. And then you go to another parameter and change that parameter. So we call it OAT procedure. So based on various scenarios, various situations that might happen in practice, you check the robustness of your model and of your product. You also need to report performance in a right way. We have a standard for this, which is TS 4213, which is a standard for reporting regression and classification indices properly when you are going to the market. So the first one is by task. You report all the indices in order to magnify your errors from different perspectives. Then you also provide deployment metrics. It's when you already design your system and you are testing it in practice, then you also need to add extra indices that are related to deployment, like latency, throughput, efficiency, energy consumptions, and everything. You must consider them too. The third one is the adding significant tests. Why it is important? Well, I will talk about it after my slides, and I will bring up some ideas why you need to provide and report significancy test results, especially the FDR adjusted p-value, which is a more efficient way to report p-value based on your small sample size. But remember, p-value is not the optimal way. You have to customize it and change it to false discovery rate adjusted p-value, which is the p-value under the assumption that your data is being used to test the hypothesis. And then the effect size. You will understand why the effect size is very important in terms of robustness. And for example, if you are working on a neuromuscular AI example, then you have to assess the performance of your method per movement, per subject, and you have to assess the robustness to noise, fatigue, electrode displacements, etc. So if we mix them and combine them together, we will have this. So the requirements is the fairness acceptance and the risk acceptance. You set it before running any experiment. Your data has to be quality assurance QA tested and QC tested before using data for validation. And you have to have a bias audit plan. There are various biases, more than 35 biases that might happen when you are using or designing your AI system, and you have to avoid them. I will talk about some of them after the presentation, okay? But you need to read the standard and make sure that you follow this, because otherwise you will be susceptible to various type of biases. And then for modeling, you consider baseline metrics, the robustness plan and results, and you have to check the fairness level. And finally, when you are performing validation, you report the consolidated risk report, and you avoid data leakage, which is very, very important. When you are working on your validation, you always need to think about the way to minimize the risk of data leakage from training to the test set. I can bring up a simple example. There are various methods in the literature to work on the MRI or CT scan data, but the problem is that there are various slices, and many of these slices are correlated to each other. And when you look at the papers, many papers that are useless, in my opinion, they don't care about subject cross-validation. So they have a data leakage because various type of data are correlated, are highly correlated. So basically they put some of them in the training and some of them on the test set, and you already have some of them in the training, so your accuracy will be 95%, 99%. But if you perform subject cross-validation and avoid data leakage, your accuracy will drop to 20%. There is another issue of data imputation. Usually engineers use methods for data imputation based on filling missing data using neighboring samples, and they virtually increase their accuracy by this imputation. There are many ways that creates biases, and we have to be careful about them. Okay. And then when you design your system, you have to go through the post-market clinical validation, and you have to check what happens to your device when the biases accumulate during time. Something that we do not consider while designing our method. So putting everything together, we will have a list of standards to pay attention. For example, the TR24029 related to robust appendix. The TR24027, it is related to fairness appendix. We also have another standard, TS12791, for fairness appendix. So they consider it from various perspectives. And the only way that you can implement them is by a statistical knowledge. This is the missing chain of engineering, in my opinion, because most of us lack this skill in order to be able to implement these indices properly. And the assessment, also the AI risk management in your procedure, and also we have another one which is related to the trustworthiness in AI, and they talk about this. Now, let's go from theory to practice. How can we implement the robustness? And how can we make sure that the robustness exists in our problem? Okay. Suppose that you have this. You have electrode of various channels. Okay. This is a typical example of our problems. And for each channel, since the data is stochastic, then you have to define features, right? For example, the RMS and mean frequency, even the entropy, anything. So you already have 3 features per channel, and you have K features, and you want to perform a classification or regression problem. Okay, you want to solve this. I would say it is a classical problem that we have It doesn't matter if you're working on EEG data or high density surface ENG or intramuscular data, you always have these kinds of structure. So something that you have is this various columns that are features of the channels. Okay, let's say you have 3 multiplied by k columns. Okay, and then you need to perform a kind of classification or regression. So from the very beginning, I call it the A matrix. And I'm going to say what will be the main problem for us. Well, we can go through some kinds of metric linear algebra. I think that is very important. It doesn't matter if you are working on gradient-based optimization, if you are working with least square, anything. We have something that should be very interesting for you. Let me write it simply, and then I go through the outcome. It can be proven easily that the norm of change of the unknown variable can be modeled by this. Okay. This is this one, the input known data. And we usually want to solve this problem, right? It is multiplied to unknown, and then you will have the output. So the amount of change that you can expect from your unknown variable is dependent on the condition number of the matrix. So the condition number. Well, if the condition number of the matrix is high, with a very small change and perturbation, you will have very high change in the unknown variable. And that's where your solution will fail, because it is highly dependent on the condition number of this matrix. Okay, a very simple example in terms of least square here. Suppose that you are working with this. It's a very simple example, okay? The condition number of this is very high, and you will know why later. So the condition number, it is called the ill condition matrix, okay? And then if you solve this simple linear, I would say the normal system, then the answers would be 0.5, 0.5. But now, if you just add 0.1 to one of them, okay? Then suddenly the unknowns will change to something that you don't expect. So these are not really similar to these ones. So a very small change to the signal will end up to a very high change to the unknown variable, which is not robust, right? So one of the conditions that are very important is to have not to have a condition matrix, okay? So if you have ill-conditioned matrix, then you are not robust. So when does it happen? One of them would be the case where your data is not standardized or normalized well. So you have a very small value here and a very high value here, but it means that your data should be normalized very well. But it's a very small condition. the main problem is the correlation of the columns. So if the columns of A are correlated, then the condition matrix of A would be high. And even without running any perturbation test, you will fail. Because this scenario is not robust, okay? You know, robustness is not just checking the variability of your input parameters. It's also about the structure and the way you think about the whole problem. So when you are using a data that is highly correlated, you will have a problem. What would be another problem? Another problem comes when you have columns that are not discriminative enough. So suppose that you recorded data from a feature of a channel and it's not significantly different from one class to another class. So I would say it's redundant, okay? So when you perform the perturbation test and you add noise to this redundant channel where you haven't identified beforehand, then your accuracy drop rate would be very high because you didn't perform a statistical selection. And how we can do this, it is dependent on your problem. For example, usually we have subjects, we have features, we have various conditions like percentage of MBC, you have various conditions, then you need to consider them and use a proper statistical test to identify significant factors. And how can we identify significant factors? By two indices. The first one is a kind of p-value which is called FDR adjusted p-value, which is more conservative than p-value. And it's like customizing your p-value to your small sample size. And many of the columns and features would not be significant after that. But even after this, we will have another pruning way. We call it calculating effect size. And what is effect size? The effect size is simply something like this. Like the mean of, for example, based on the mean of the variable in two classes divided by the variance of the feature. So basically, the higher the difference compared to the variation, the higher the effect size. And we will have a small effect size, medium effect size, and large effect size. If you want to have a product that is robust enough and will pass the perturbation test, you never use features that have the effect size less than medium. So you always consider those that have medium or large effect size, and you select them, okay? And you go to the next step. So first of all, it's a pruning step. You just select those features that are discriminative enough, and you make sure that they won't fail when you will run your perturbation test, because you have to add noise to the input. You have to create some shifts from channels. You have to simulate other condition or using scenarios for cross-sensor validation. Okay, so those that have a small effect size, those that are not significant, they are not good features for you. They only increase the dimension of the data without increasing the amount of information. So basically, you will end up with the curse of dimensionality, but you will have a problem that your dimension is not representative of your information dimension. Okay, so the first step is this one, and you have to use proper statistical model like generalized linear model. If you need to use random effect, if you don't need to use random effect, you have to use another test like GEE. There are various types of statistical tests that could be used here. Okay, so first we run this test, and then we go to the next step. The next step is to think about the correlation between features. One way is to remove those that are highly correlated, which is not good because you will lose information. And especially in this scenario where these features already pass the very conservative approach. So what should we do? We perform the PLSR algorithm, which is a very nice algorithm for high dimensional data. It's like running factor analysis and then using least square on the selected factors, okay? So we perform factor analysis, and each factor is a combination of the features, okay? And then you perform least square or any type of classification regression on the factors rather than the input features. So we perform least square on the factors of the signal, of the features. And if you want to have explainable structure to focus, for example, my factor number one is the mixture of this feature and this channel is located especially on this type of brain, and you want to map your output, your selected features to, let's say, a specific orientation or spatial location, then you have to perform rotation, okay? So when you perform rotation, then your factors will only have a specific type of features without any overlap. So you are able to name your factors properly. And what is factor analysis? Is a type of PCA that is a result of the SVD, okay? So it's the best way to perform robust PCA using singular vector decomposition, because with the SVD, you can also calculate the robust PCA. So instead of traditional PCA, where we perform eigenvalue decomposition, we center the data, we project the matrix, etc., we perform SVD, and we make sure that we center the data, and then we calculate the SVD, you know, it's like this. And then it has been proven that based on the result of the SVD, you can have also the PCA, but in a robust way. So you classify your PCA components, but they were not created by traditional eigenvalue decomposition. They were created by the SVD, okay? And then you perform least square or other types of classification or regression. Okay, so at the end, if you want to be robust, you have to choose your ML method wisely. If you want to choose them wisely, you should pay attention to math and theory. You know, the worst way is to just run your ML algorithm and use try and error to see which one is better. Because I would say even high school students now running Python. They can write code in Python, and they are in this primary school even. But what is the difference between engineers and top engineers? Top engineers know the math. They know statistic. And then they implement it in their with their engineering skill in order to be better than others. So from robustness, we came here to the condition number of the matrix. It can be easily proved. You can easily prove that the condition matrix, the number of a matrix, will have the effect on the convergence of any gradient-based algorithm as well. So it's not just like least square. So even if you are using gradient-based algorithm to train your neural network, deep learning, etc., the convergence of this is highly dependent of the condition number of the matrix. So the failed procedure is just to give data to deep learning algorithms and say you will have output. Of course, this is not true because they mostly fail the robustness test. And why is it important? It's important because when you design something in the lab, it should work in practice, where the situation changes, the temperature changes, the electrodes might drift, and the measurement noise will change. So if you want to make it work, you need to use proper methods and validation methods in order to be robust enough, okay? It is also another standard for bias. I really recommend you to get access to this one and try to read this one. This is a type of bias that you should pay attention when you are designing your system, no matter if you are working on classification or regression, okay? And they are demographic parity, and you can implement a statistical test to prove them for your device, you know, because now they are talking that AI algorithm, they have a lot of biases from clinical and methodological perspective. So the performance of your system should be consistent when talking about various categories of your data. And it requires a specific statistical test, I would say from z-test to the chi-square test of homogeneity. Predictive equality is another one. Today I was supposed to talk about robustness, okay? But I just bring you some keywords so you can check later. We have various types of biases like demographic parity, predictive equality, equality of opportunity, and equalized odds. And you need to read the standard, and then you need to see which statistical test should be used in order to prove that your algorithm doesn't suffer from various types of biases.